started, we are going to deal with climate change in the first half. Second half, I will introduce you to ENACT briefly, and then show you some of the map rooms available for the ENACT's countries, some of those which are working. Okay, now, before I go to today's topic, anybody with any question from what we did yesterday? In case you went home and you said, okay, maybe I should have asked this question. So in the chat box, you can share any questions related to what we did yesterday. Okay, no? All right, then. Hello, Tamu. Tamu? Terus mana Tamu? From Makerere University. Okay, so let's start then. All right, let's do climate change. At last, we will end with the week with climate change. See? So these are what we are hoping to accomplish today. Understand some concepts about Earth's energy balance, water atmospheric windows, greenhouse gas are important. I think everybody knows by now. What are the man-made things? The thing is man has done to screw up the atmosphere, the Earth, the climate, the planet in general. What are some of the impacts of climate change, and then what is the difference in climate change and global warming? Maybe the same. Okay. So let's start with I think we defined the last time. Remember on the first day when we tried to define weather, climate variability, climate change, we defined climate change as change in the very long term change. So two keywords. Number one, change in the characteristics of climate. That's very important because many people think climate change is the change in the mean. Remember, they show you the increase of something, the temperature over last how many years, and okay, that's climate change. Yes, that's climate change, but that's not the only thing. Characteristics involves a lot of things. And number one, that's the first concept. And of course, the next concept is over a very long period of time. So it has to be over long. It's not 5 years, it's not 10 years, it's not even 20 years. It's a long time. Because it's a change in the climate. And even we said we define climate using 30 years of data. So climate change is measurable. So climate change might be manifested itself in variation in global or regional or even local sometimes. So the impact of climate change, especially from the climate perspective, is different over different parts of the world. So that is one thing. And again, reflects change over time. This is the same as what we said before, and occurs in, of course, very long time period. Okay, that is climate change. So if it is sunny today and tomorrow it is cloudy, that's not climate change. That's just weather. Now, so by now you have very good understanding and you didn't mix up climate change and climate variability, which we covered in detail the other day. So sometimes we see climate change. I mean, if this is probability density function, And this is how climate change might happen, right? So the dotted line is the climatology. What do we have if there was no climate change? And the dotted lines are what happens with climate change, the different things that might happen. So the first one, this one, is the solid line is the what we call the climatic location, but the climate change might shift it, might shift this to the right, which means is that increase in rainfall. Okay, you see that's why increase in extreme events in this case also, but also change in the mean. This is a shift in the mean. The whole distribution is shifting. It's not just one increase, but a shift, the whole shift. And that shift includes the shift in the mean, but also you can see shift in the extreme event. So more extreme or could be more hotter or more rainfall or more of what normally happens. Okay, shift in the mean. The other is, you see the mean is the same. I mean, the mean for this solid curve, and because just looking at the mean, you can see if you are, this is normal distribution. So the mean is in this case hasn't changed at all. It's the same mean. Okay, the same mean, but you can see a spread, wider spread, with because of climate change. Now, what is increasing is the variability. So in this case, the year-to-year variability is increasing. So increasing the mean, now increasing in the variability, which means here is see here it was a shift towards one side, but here both low values and high values increase. So which means it is 1 year it could be flooding, another year it could be drought. So that is what it says. This one is saying increase in variability means increase in extreme climate events. Uh, I mean, another thing is just what we call symmetry, skewed symmetry to one side. Okay, so one event happening more than other event. Like either here if it is cold here, it is hot here. You can see the distribution a little bit now. The mean has changed because this time the mean has shifted to the left. You can see it, but also there is some shift in the distribution. So all this, the whole idea here is all these constitute climate change. Okay, not just one. Any of this could be climate change. Okay, or combination of, by the way. You can have increased variability along with increased change in the mean at the same time as well. So combination of things, but this is to underline climate change is not just one thing. It's not just increase in the mean, which is but only the top one. Okay. And here we want to underline, we are talking about man-made climate change, not what happens naturally. Naturally, every how many years things can happen. We had ice age, we had this age, we had that age, but that was not man-made. That was God-made. But this is what we are talking about: human being screwing up what God has created. Okay, if you're religious. Now, the other is, so we know climate change, but people are also talking about global warming. What is the difference between climate change and global warming? Here I will take about what, 1 or 2 minutes to hear your response. David, can you help me because the screen is, can I actually look? Okay, actually I can check now. Let me see, what's the difference between climate change and climate variability? Come on. Okay. So let me look at the chat if anybody is responding. So only in the chat, I'm not asking. Okay, in chat box. Okay. Anybody want to tell me what the difference between climate change and global warming, or is the same thing? You can also say it is. C'est la même chose. By the way, you can write down in French if you want. Global Celsius says global warming, it is an increase of temperature over a long period of time. Okay, what about climate change then? Uh, Margaret, global warming is the rise in global temperature. Okay, what about climate change then? Install. I mean, everybody talking about global. What about climate change? You have to contrast what's the difference between climate change and okay. What David says, climate change refers to long-term shifts in global weather patterns. Okay, while climate. No, no, I didn't ask. I asked you the difference between climate change and global warming. Gabriel Cross says global warming is an old term to mean climate change, but science agree to. So Gabriel Cross says the same thing, just old meaning. Moses, climate change. Come on, climate change is the long-term variation in climate. Global. Come on, global global warming is an example of climate change and is especially related to. I mean, I think Gabriel Cross, Moses close enough. Irene, oh, is a long one from who is this? From long one from Sabela, my favorite name. Global warming. This specifically refers to the long-term increase in Earth's average surface temperature due to phenomena, particularly climate change can result from natural process. Yeah, but we said we refer to only man-made. When we talk here about, it's only about climate. I mean, man-made climate change. As I says, global warming is one of the consequences of climate change. Maybe. So, climate change is the change of many causes in climate over time, and then so global warming is one of the variation of climate. Okay, one aspect of climate change. David, global warming refers to the long-term rise in average surface temperature, global warming, okay, on the Earth, while climate change is not only warming, but also other changes the Earth's climate. I think I like what David put. All right. So anyway, here is the difference. Okay. Global change, I mean, climate change refers to anything that results in different climate across the planet, which include long-term average global temperature or precipitation decrease or increase. So it is all the impact, but global warming is, as Elsabe said, is just one aspect of climate change. So climate change is more than, I mean, climate change is more than just global warming. It's one just one aspect of global warming is one aspect of climate change. I think many of you got it right. Now, so what causes climate change? Okay, what is the cause of climate change? So here, I'm saying climate change occurs when there is an energy imbalance, where energy imbalance happens to the planet, to the Earth. Normally there's energy balance, but if that energy balance is disturbed, uh, that is one cause. So and this energy imbalance occurs because of two reasons, right? Either more energy is coming in or less energy is going out. Uh, the air, the first day we discussed the fact that the sun is our source of energy. Okay, so that's the incoming energy. Uh, I don't. Do you believe we are getting more energy from the sun these days? Maybe not, or less energy going out. So this is normally the balance. So the red arrow is energy coming in, that's from the sun, solar radiation, and blue is energy going out. And so here the two arrows are equal, which means the energy comes in and then the energy that goes out in one form or another. I mean, or on average, otherwise the energy stored, energy, a lot of things. But sometimes this happens. So either the energy, if you see either the energy coming in is bigger, which is the brown one, or the energy coming out is smaller. You see that small gray arrow here, this one. So for the Earth, for our climate change, which one is occurring? The first one, more energy coming in, or this less energy going out? Right? I mean, we say it is because, I mean, this is an exaggeration, but it's because of less energy going out, less than what normally goes, less than this is what we have, but now you see this is what we have, but now you have only small amount. This is a cartoon just to describe what the issue is. The issue is we having more energy remaining in the Earth's atmosphere, and that more energy has to do something. It's energy, and energy does things, right? So that's what the whole thing is about. Warming. We'll see what that energy does. So this is a question: what happened to the extra energy in the Earth system? So now if we agree, assuming we agree, that the whole climate change issue is less energy leaving the Earth's system, which means there is more energy remaining in the system, right? And so what happens to that energy that supposed to go out, but now staying in within the Earth's system? So there are many things that can happen. So the first thing is, of course, increase in temperature. You know, the Earth's temperature, they say 1 degree, 1.2 degree, 1.5, whatever degree. So that is what we call sensitive heat, which means the heat, the energy that you can sense as temperature, as the surface temperature, atmospheric temperature, water temperature, or whatever, the heat that we sense. The other one is an energy that we cannot sense. That's what we call latent, which means hidden energy. Because if to evaporate water, you need energy, right? Well, that's what we call latent energy, because the evaporated water contains energy that converted it from liquid to vapor. Or that energy can go into melting ice. Again, we cannot, so that kind of latent energy. The other one is dynamic format. That energy could be converted in dynamic. Dynamic means what? Movement, right? That could be winds, ocean currents, surface waves, all those kind of moving things could be converted to that. And another one is could be stored in the ocean's temperature. So if you just keep warming the temperature, I mean, the ocean is huge, so it can take in a lot of energy and could be stored as ocean temperature. By the way, the ocean temperature, if you are following the news, there is huge hurricane, which is cyclone, that is hitting the southern part of the US yesterday, today. Is very, very strong. And there was a forecast a couple of months ago that this cyclone or hurricane season in the US will see more hurricanes and stronger hurricanes because the ocean been warmer over the last year. You see, so that warm energy, that stored energy as ocean temperature, sometimes manifests itself as cyclones, hurricanes, typhoons, whatever. Okay, so that is what happens to that energy. Maybe there are other things also. These are just the main ones. So we said what are the factors that affect energy going outside, I mean, leaving the Earth or not coming in. There is this concept of atmospheric window. Okay. So let's take another 1 minute. I know I want to know what is an atmospheric window for you. Have you heard of atmospheric window before? And what is it? So we'll take about 2 minutes from you about this one. Atmospheric window, elaborate. Well, I'm asking you to elaborate atmospheric window, design. So, what? Okay. It latest incoming energy. That's a window. Okay, at least one thing. Anybody who Kelsey tried, it says it's lets incoming energy in. Okay, that's possible. But why the window? Mm. Phantom, I don't have an idea. Phantom doesn't have any idea. I think that's honest, is good. Greenhouse gas concentration. Greenhouse concentration? Atmospheric window. It's a window. Atmospheric window, greenhouse gas concentration. Okay, anybody else? David, the first specific wavelength range in the air is it seems like David is Googling something. Hmm? This allows radiation. Okay, I think I like David. What that? Adukpos. Uh, what? Gabriel Kedan says it is. Okay, Ronald says can I get it from ChatGPT? Maybe you can check. Moses says point of the atmosphere where radiation cannot be absorbed. Okay, close enough. Elizabeth says ozone. What has to do ozone and maybe okay. Or I have to atmospheric window that sun rays pass through. Okay, I mean that the sun pass through everything. Otherwise, we wouldn't get the sun. No? Almost. Uh, Kyoto, a place with limited or almost no absorption by the atmosphere. Okay, I think that's a place where limited or almost no absorption by the. I think that makes sense. Coyote. Emmanuel, it's vegetation cover. Come on. Boma, point where air going out and air coming in. I like it. Okay. All right. Let's see what the definition is. Atmospheric window. So it says bands of energy. So a band of energy is measured by either wavelengths or it is frequency. And any electromagnetic radiation is described either by its wavelength or by its frequency. So in this case, it is wavelengths. So energy that are able to pass through the Earth's atmosphere. That's it. So it is not actually it is not about the atmosphere, yes, but atmosphere, it's also the radiation that passes through the atmosphere. So if you look down here, it says wavelengths in micrometers. So from here all the way to whatever 20 micrometers here. And on the vertical, you see how much energy is absorbed. Okay. And actually, what's shown here, the molecules here are what absorbs that energy. So energy in these wavelengths, you can see from 0 point something to almost 0.3, is all 100% absorbed in the atmosphere. By what? By oxygen and ozone. By the way, if this energy is not absorbed, actually it is very harmful to your skin. Okay, this is because this is the ultraviolet radiation. Ultraviolet radiation, and ultraviolet radiation is bad. Remember how many years ago, maybe before you many were you born, there was about the ozone hole. Okay, so the ozone hole was about ozone being depleted, I think in southern hemisphere somewhere, because ozone was depleted by pollution. So if you don't have, what does it mean? If you don't have ozone here, this radiation will come in. If it comes in, it will harm you. That was the whole issue of, at one point, there was a panic because of ozone hole over southern hemisphere. And now, by the way, this is one of success actually. Um, they changed what they use in fridges and other whatever things they use. And since then, the ozone layer has been back. So it means it shows that we can change things. So the other one, all the way from 0.3 to maybe not near 1, uh, is the visible light. This is solar windows. Solar window means this is the window through the energy from the sun mainly comes in, at least what we see. This is that pan. Okay, so that comes almost 100%, right? I mean, there are things that affect, for example, if you have water vapor, H2O means that is water vapor in the atmosphere. It might absorb some of the solar radiation, right? When it's very cloudy, when it is whatever, low to atmosphere, water in the atmosphere can affect. But you can see it's mostly, it can come down. That's why we are here on Earth, by the way. If this doesn't happen, then we will not be here. Or maybe it's different kind of living things. And the other window is this one, okay? And this one. Again, here it's almost, this is atmospheric window. I mean, this is like where radiation from the Earth can go out. Again, here you can see some absorption again by ozone. Otherwise, it's mostly it's not absorbed. After this, it is totally absorbed, so it cannot go out by carbon dioxide and water molecules. And you can see here also some carbon dioxide and water molecules playing the role. So here it is very important to see what carbon dioxide is doing here, what carbon dioxide is doing here, along with the water vapor. Water vapor can change, right? Water vapor cannot stay in the atmosphere that long because it rains, it dries, whatever. But the carbon dioxide thingy can stay. So you can see what happened. Okay, so that is all about atmospheric window. Is very important. Why? This is for the incoming and this is for going out, and you can see what the different gases or molecules are playing. Okay, hopefully you understood what atmospheric window is. So now let's talk about greenhouse effect. If you know the window, now let's talk about greenhouse effect. So because before we talk about greenhouse effect, what's a greenhouse? What is a greenhouse? You are agricultural people, so this should be easy for you. Can somebody tell me what is a greenhouse? Is it a house painted green or what is it? In the chat. Link to all presentation. Chris, I asked you what is a greenhouse? Greenhouse vegetation cover? No. Glass house. Okay, I want to say greenhouse is a glass house. Anybody else? What's the greenhouse? Okay, what's a greenhouse and what does it do? What's the purpose of a greenhouse? Normal, just Baroque says what? What is it? It is a house of green plants which made of a glass. Okay, what does it do? Why? What do we use a greenhouse for? Who is this? The guest says what? Where certain gases like come on, scroll too fast. Trap heat from the sun. Nah, not sure. These are greenhouse used for plantation within a controlled condition. Yeah, what is being controlled? Energy controlled chambers, it says Ronald, okay. Some level. The structure with controlled environment. Yeah, exactly. So, but what is control? Yes, the controlled environment. But what is being controlled? Yeshamble, Yeshamble, Yeshamble says climate condition in maybe okay, climate, the climate, yeah. Temperature, says Emmanuel. Vegetation? No, it's not. Yeah, but it's not to control vegetation actually, but yeah. Boniface's trapping of heat energy by greenhouse gases. Now I'm talking about literally the literal meaning of a greenhouse. Boniface, not what we are talking about. Mahile to regulate temperature and humidity. Yeah, I think that's what they do. Okay, and anyway, I think yeah, these are kind of L-static. The plant are grown under cover of plastic or glass, and the heat from the system or plant is kept inside. Yeah, that's the whole idea. Okay, that is the thing, the whole idea. So the whole idea of greenhouse, the greenhouse is so to it lets in solar radiation, but it traps energy going out, the thermal, what we call thermal radiation. Remember, is the other day we said the source of energy is sun, but also the source of heat for is surface of the earth. So the glasses can trap heat. I think a good example is for this is a car that is left outside in the sun, right? If you have a car and you park it outside and go for shopping and come up out after an hour or whatever, the inside of the car will be much warmer than the outside of the car because your car, the glasses in your car can let in solar radiation, but they keep the thermal radiation that's going out. So you're, in a sense, your car is a greenhouse at that. So it's just letting in solar radiation, shortwave radiation, and trying to trap what we call thermal radiation, long wave radiation. Okay, so now that is greenhouse. So the greenhouse effect is that kind of effect, but now not a car, not a greenhouse, but actually the whole of the atmosphere. So in the sense of the atmosphere, this is what we call a greenhouse effect. Now, for your car or for the greenhouse, the heat is trapped by the glass. But in the atmosphere, the heat is not trapped by this thing here. You see by the not only but the carbon oxide and those of the what we call the greenhouse gas effect. So normally radiation coming from the sun goes into the atmosphere. Some is absorbed, some is radiated back. So and you can see infrared released by the air, some goes out and some comes back. So if you have more of this coming back to the air, that is what is heating in the atmosphere serves as a greenhouse. Now, I think maybe another example, good example could be from the atmosphere perspective. If you compare a cloudy night, okay, compare a cloudy night with a clear night, cloudy night, clear nights, which one would be colder? Can somebody tell me? Again, in the chat, if you have, okay, clear night, okay, why clear, I see many of, why clear night? Nardos, why clear night? Yes, it is clear night will be colder, but why that? Cloud trap, yeah, actually that's right. So because in this case, the cloud serves as the greenhouse, creates a greenhouse effect because that radiation that goes out, if there is no cloud, that energy will escape into space. But if there are clouds, that energy, some of part energy will come back. So this part here, some of it will come back. And the thicker the cloud, the warmer the night will be. Because if you have thicker cloud, more energy comes back. If thin cloud, less energy comes back. So it is the same now for those. Now, instead of having a cloud, now we have carbon dioxide, we have methane, we have this, but it's mostly carbon dioxide, because we always had carbon dioxide in the atmosphere, right? But the issue is it has been increasing. So I mean, these are the greenhouse gases, remember? So ozone, nitrogen oxide, water vapor. We have seen water vapor, its effect in many cases. Carbon dioxide, methane. And so these are the main ones. There are other those ones. But now we are focusing more on carbon dioxide, because that is because it is being emitted, released to the atmosphere over and over again. So normally, this is the carbon cycle. Okay, so the vegetation releases carbon and absorbs carbon, the same for ocean. This is natural. If you don't do anything, this is natural, it's fine. But this is what now we bring in as human, right? So normally there is a balance. Yes, we always had carbon dioxide in the atmosphere, but there was some sort of a balance. But then we came in, these two-legged animals, and did a lot of things, too many buildings, too many cars, factories, all that led to increase in carbon dioxide. So this is again showing you carbon dioxide over many years, right? The concentration, and then every year, starting from 1900, how much. You see, even before 1900, there was carbon dioxide in the atmosphere, the brown line. But recently means after 1900, whatever the West calls the Industrial Revolution, then carbon dioxide suddenly starts increasing. So which means, by the way, it is like equivalent to increasing cloud cover during the night. Okay, now you have carbon dioxide. Cloud comes and goes. But carbon dioxide, it stays. That's the issue. It stays in the in the atmosphere. By the way, even if you stop emitting carbon dioxide today, we will have a lot of carbon dioxide for many years to come anyway, because it stays in the atmosphere. That's the big challenge, the main challenge. Okay. So the impact is, of course, there are a lot of impacts again, rising sea levels. Okay. Of course, more worse droughts, or more, worse droughts or worse flooding. Rising temperature, more or worsening what? Storms. So we said hurricanes, typhoons, cyclone, forest fire because it's too much, animal extinctions which cannot cope with the new climate, and health related, more heat related illness, but also more um, vector-borne disease, right? Climate can result in more. So malaria might expand into Europe eventually if the temperature stays, continues. That kind of thing. Things that were limited to tropics now can expand to extra tropics. And so many other factors in terms of the impact of climate change. So the other day we talked about weather forecasting based on initial information. We talked about climate prediction based on boundary condition, what like sea surface temperature. But there are also climate change projection. So it is not a forecast, it's not a prediction, it is a projection. We use models, the same as models we use for the climate, but in this case, it is based on what the atmosphere will look like, which in a sense, how much carbon dioxide and how much pollutant we will have in the atmosphere. So we don't have that data, right? We don't have data about greenhouse gases in 10 years, 50 years, 20 or 100 years. So we don't have the data. Okay, we really don't know exactly what will happen. So what do? We do scenarios. We say, if this happens, if that happens, and many of you must be familiar with this scenarios. If you stop today, if you decrease by this much, if you decrease by that much. So these shared socio-economic pathways, SSPs, I don't want to go into. So this is the whole idea of, at the end of the day, how much pollutants, how much greenhouses we will have in our atmosphere, in whatever, from today until 2000, until 2100, you see here. So until where we are, you can see the temperature increase. This is just temperature, by the way. So this is more what we call a global warming aspect of it. So it depends what happens in about 100 years will depend on how nice we are to the earth, to the planet or not. Okay, how considerate we are for the future generation or not. So that's why. So that was called projections, and because it's projection, it got a lot of uncertainties, a lot of. By the way, those gray shades, they show you the uncertainty. So yeah, you have to see the line, but actually it could be anything anywhere within the shaded areas. So there are many people who believe the climate projection, take climate projection data, rainfall or whatever, and then put it into crop model and say, okay, in 50 years, this is what will happen. For me, I will not advise that because the data is low. So you have to be really very cautious. It's not definite. You have to say there is chance of this, chance of that. Okay, even the data is set, even for temperature. If you look at the rainfall, by the way, it's even more uncertain because again, it depends on something we really don't know in the future. Okay, makes sense? Maybe. So now that was climate change, but we talked also about climate variability, right? What's the difference? Of course, it is issue of time scale, right? So this, for example, climate variability. You can see the whatever this parameter, let's say rainfall. You can see year to year variability. So this is some year is up there, some year down there. But what about this? You see? So the first half is mostly about climate variability, but the second half you can see now the variability is still there, but also there's something happening at the same time because it is going in the first half, it is within a bounded environment, bounded situation. But in the second, you can see we don't know where it's going to happen. So that's one way of understanding climate change. But also, how do you compare climate change to climate variability? I mean, for a given location, can you compare the impact of climate change to the impact of climate variability based on data over the last how many years data you have? Yes, you can. There is an IRI, what we call MapRoom, that where you can have a look at that one. So this is temperature observation for some location in Colorado, here in the US. So here you see both temperature and rainfall. So you take it at the data, okay? You look at the data, and you see variability, year-to-year variability, what we call decadal variability, then climate change time scale. So for temperature, for that location in Colorado, the impact from climate change is about 12% of the whole variable. Because the year-to-year variability, what we call decadal, 10-year variability, and the climate change, in your data, they don't appear separately. They are combined. It's what's called. It's a compounded effect. But there are ways to try to isolate those different impacts, complex impact into its components, climate change, decadal variability, and year-to-year variability. So for temperature for Colorado, you will see most of the variation comes from the year-to-year climate variability. For temperature, actually, even more. Actually, for rainfall. For rainfall, most of the impact comes from the year-to-year variability. So it's good to have a perspective. If you do this in places for Africa, actually, we can look on a map. So this is uh, climate trends. So you can see it is mostly low, right? I mean, in many parts, the contribution from climate change. There are areas like West Africa where it's almost 20 something percent. So you can Europe, Northern Europe. This for climate change trends. This is what we call decadal variability, which decadal variability means this is something that happens every 10 years, 15, 20 years. That is how the cycle. So you can see that happens, of course, more frequently, but also shows as having significant, and you can in some areas up to 30, 40% contribution. If you come now to year variability, voila. I mean, the white areas you see on Africa is because there's no data. Otherwise, you can see up to 80% of the variability comes from this year-to-year change extremes. It's good to have some perspective. But what you see normally, what you observe is not an isolated component, but it's a compounded thingy. But it's good to have some perspective in terms of, like I said, hurricane this season here in the US is supposed to be more and more frequent and more intense. So is it because of the year-to-year variability? Is it because of the climate change? Is it decadal? It could be all those combined together. Because normally they don't happen in turn, okay? It's good to understand the complexity of the thing. Okay, that is all about climate change. I think you now have some basic concept, hopefully, basic understanding. Of course, we can spend the whole day on climate change or the whole week if you want to. But I think we are wanting to focus on the basic concept. Now it's time, your time to ask questions. Again, please only in the chat box or raise your hand if you want to. Any questions? Climate change is imbalance of energy, which means the incoming energy is greater than the energy back from the earth. What happened? The energy come from the sun is less than the energy. Who is that? That says, what if the sun sends out less energy? I think the sun will keep sending almost the same amount of energy for the next how many years is it? 1 billion years? I don't know how many years. Okay, so we don't worry about the energy from the sun decreasing. Not in a, I don't know, not in a billion years, I think. I don't know how much people know. How much will sun expect to last? Does using GC, Henok says, does using GCMs or ensembles minimize the, I mean, using the ensembles definitely help us to minimize the uncertainty. Always using the average ensemble is there. James, you got, where is James going to go? Okay. Can global, come on, can global warming reduce? Is it reversible? Yes, of course. I mean, we are the ones screwing up. So if you want to stop emitting atmosphere, it takes time, by the way. It cannot happen right away. Remember I said we managed to stop ozone depletion. Man, was able, or we were able to stop ozone depletion. So we can do the same for this thing. It's just, number one, try to decrease the amount of carbon dioxide going into the atmosphere, but also find a way to extract carbon dioxide from the atmosphere. There are now different technologies called, what's called? Carbon sequestration, whatever. But there are ways. So yes, you can do, there are things you can do. What's the difference between global warming and global boiling? What's boiling? Around, huh? What is the basic difference between No, I think they are just different names. They used to be RCPs, now they are called SSP. So maybe you know more than me about that, but it's just an improvement of a change over there. So why does carbon dioxide stay in the atmosphere? That's a good question. Why? Because for something to disappear from the atmosphere, it has to interact with something, right? But carbon dioxide seems to be very stable, right? And ozone, for example, might be into oxygen or something. And of course, water vapor doesn't stay in that long in the atmosphere because it evaporates, it rains, and all that. But carbon dioxide is more stable because it's not interacting with anything in the atmosphere. Ask about the term climate sensitivity. Are some green agree more sensitive to rise in temperature? What? Are some agree more? I don't know what the question is. What was that? El Sadiq. But yeah, there are some things that can heat faster, and some, for them, the ocean doesn't heat faster. The ocean just keeps absorbing the energy while the earth can heat faster. But for heating faster, by the way, also means losing the heat faster. So the seesaw. Will you tell us what is climate change? Okay. Can you recommend me programming that does EOF? EOF, I don't know, you can go to IRA data library. Okay, IRA data library file, Google, that is for Kazan. Google IRA data library, and one of the things it does is it can do it for you. That's outside the climate change. Let's stick to climate change. Do you expand more on global warming potential for greenhouse gases? Yeah, so like I said, remember, if you compare a night with thick cloud and thin clouds, the night with thicker cloud will be warmer because more energy will come back. So now, instead of the clouds, you can think of greenhouse gases, carbon dioxide. So the more carbon dioxide we release into the atmosphere, the thicker that greenhouse layer will be, which means it will return back more and more energy, which means making the earth more and more warmer and warmer. Uh, I mean, because Tata talks about uh, natural versus anthropogenic. 99% of scientists with the right mind think it is anthropogenic. What happened? I mean, you have to compare. Okay, if it's not carbon, we know carbon dioxide has been increasing over the last 100 years, right? Okay, we know. Okay, and we know what carbon dioxide does, right? It's a greenhouse gas. So it has. What else happened? I mean, if you want to call it natural, you have to come up with what is the natural cause you think has happened to change temperature over the last 100 years. So yeah, definitely, I think at this point there is no doubt about the anthropogenic effects of things. Rahel, what are the cause of climate? Rahel, you're asking me what the cause of climate variability? We talked the whole day yesterday, no? Maybe Rahel, you were not here yesterday. Okay. All right. Uh, what do we have here? So, David, before the break, can we do the, no, forget, can we do the survey thing? In the meantime, you can ask your question, but also do the survey. David, you are around?
Yes, yes, yes.
All right. In the meantime, those people can also do survey and also ask questions. Let me see. Tarek, which what? So I like the question from Onyed Kachi. He's saying, why not the carbon dioxide go outside? I mean, he want to get rid of the carbon dioxide by letting it go to the space. So he's saying, why do they hang out? I think the number one is that, the what, but by the way, if it's true that the gas in the atmosphere could escape into the space, into the vacuum, then oxygen, everything will go into the space. Okay, then I'm not sure whether there will be life here, especially life, because if carbon dioxide goes, oxygen can also go. Okay, so the one thing is the Earth's gravity uh, keeps things around. I mean, the whole atmosphere, not just carbon dioxide gas, but the whole atmosphere is kept closer to the Earth, partly by the Earth's atmosphere, its rotation, that kind of thing. Otherwise, if we, like I said, if we get rid of carbon dioxide by letting it, I don't know, by some magic into the space, then we might go to space along with it. What is the role of livestock in global warming? I think maybe you know more than me, but yeah, I think that something to do with methane, whatever, but for me, not into that. What is carbon trade? Yeah, I mean, carbon trade is I think it's actually more of a permission to pollute the atmosphere. So you pay something and then you get permission to pollute the atmosphere. Or maybe, or plant by doing something else. For me, I'm not a fan of it, but at least for people, for countries, the whole idea is if they pollute the atmosphere, can they pay for it? That's all I think. That is my understanding. So a good question from Intizar. How much of the change in temperature over the last many years how much has that affected the climate? That's a very good question. Okay. Uh, do we see more extreme climate? Do which means droughting? Do we see stronger La Niñas El Niños? Do we see stronger hurricanes? Or cyclones or typhoons? Do we see rise in sea level? Do we see melting ice in the north and south? Oh, yes, all those are because of climate change. I think the most dramatic one is that you see there's a lot of ice melting Greenland, well, Arctic Circle. So you see that temperature, remember I said that energy has to do something, and it already started doing a lot of things. Mm. What happened to the, okay. All right, so now let's take a break. Yes, Gazani is asking for a break. So it is 10 past hour. So in 15 minutes, we'll be back at hour 25. Okay? We'll see you in about 15 minutes.
gases. You've probably heard these terms before. Perhaps you already know a bit about them and have formed some opinions. And for good reason. This phenomenon could have some big impacts on your life in the future. Or could it? Let's go over climate change, how it works, and what it's all about. Climate change, formerly global warming, is a broad term for the Earth's overall climate warming at a faster rate than predicted by climate experts. Anthropogenic, or man-made climate change, is a more recently used term because it might be related to human activity. When we talk about climate change, we usually mean over the past 200 years, since the start of the Industrial Revolution, because that's when we've seen the biggest spike in temperature. Now, some of you may be thinking, the climate has always been changing, and that's correct. Earth has actually been warmer than it is now hundreds if not thousands of times in the past. Last time it was about 8 degrees Celsius warmer than it is today, and this lasted for over 200,000 years. And, believe it or not, we're actually at the tail end of an ice age right now. So with all that being said, why should we care about the planet warming? Well, see, it's all about the rate of change. Earth may have seen higher temperatures, but rarely has the temperature spiked this quickly. Currently, temperatures are rising 170 times faster than what scientists have predicted. Something must be causing this sudden rise in temperature. But what? Let's look at our options. There are a number of things that affect our climate, such as El Niño, the ocean conveyor belt, which is the flow of water in the world's oceans, and circular movements of air called Hadley cells, which cause the trade winds and the jet stream. There's also the tilt of the Earth's axis, which causes seasons, as well as albedo, the amount of light and heat a surface absorbs based on how light or dark it is. All these factors impact climate, but one that really needs our attention is an increase in greenhouse gases, especially carbon dioxide. Greenhouse gases are likely the biggest contributor to global climate because they trap heat in the atmosphere, and higher concentrations of CO2 have been correlated with higher temperatures. Carbon dioxide, or CO2, is one of the most prominent greenhouse gases on Earth. It's not the most powerful, that would be methane, but it is the most widely emitted and is seeing a large increase. Carbon dioxide comes from a lot of places, such as volcanoes, soil, oceans, and animals. Even cows release greenhouse gases like methane when they burp. Plants are great at reducing CO2, as they consume it and release oxygen during photosynthesis. But humans are a new source of CO2. We've invented machinery like cars and power plants that burn fossil fuels like coal and gas, releasing CO2 as a byproduct. Agriculture and livestock also dramatically affect landscapes, especially forests, as they reduce the number of native plants that would normally absorb and store CO2 from the air. So temperatures have been going up, and CO2 levels have been going up. But how can we be sure that it's our carbon dioxide? Well, for one, just like the warming, the start of the CO2 increase coincides with the start of the Industrial Revolution, about 200 years ago. CO2 levels in the air also seem to change according to energy usage. Here's how CO2 levels change over the course of 1 year. Notice how the levels drop during the summer in the northern hemisphere, when plants are more active. Then, in the winter, CO2 levels rise as the plants lose their leaves and people use more energy to keep themselves warm. Okay, but what if this is just a coincidence? What about volcanoes? Well, consider this. Carbon atoms have several versions, or isotopes, and different isotopes are made by different sources. Carbon-12, or C12, is the most common isotope, and is the type of carbon that plants use, while C13 and C14 are produced from inorganic sources like volcanoes and radiation. Now get this, we've seen a smaller proportion of C13 and C14 compared to C12. This means that more C12 is being released into the atmosphere, and there's a good chance it's coming from fossil fuels, which are made from ancient plants. Scientists also measured an estimated CO2 output from volcanoes across the globe, both surface and underwater, as well as output from fossil fuels, and discovered that volcanic emissions are about 1/100th the amount of anthropogenic emissions, and that's being generous. That's a lot to take in. But what about solar flares? The sun does go through predictable 11-year cycles with increased heat and UV rays, called solar maximums. But it turns out only a small fraction of the extra heat from solar maximums makes it to the Earth's surface, and these bursts are minuscule compared to the heat the sun produces normally. All right, let's just say that it's us. So what? What does the Earth warming actually do? Well, actually, quite a lot. Let's start off with the obvious. The ice caps are melting. Most of this ice lies on top of the water, but the rest can be found on land like Greenland and Russia. When this ice melts, it falls into the ocean and raises the water level. Water also expands under warming conditions, causing sea levels to rise even further. Rises of even 6 inches can threaten coastal cities in Florida and Louisiana, especially during storms. Snow melt on ice caps and mountaintops also shrinks habitat for many species, like polar bears and chinchillas. Speaking of habitat, another big effect is what we call range shifts. Basically, animals and plants are moving farther away from the equator and closer to the poles, which has all sorts of consequences. Planting zones are shifting northward. Just look at these USDA garden zone maps from 1990 and 2012. Venomous species like black widows and brown recluse are also expanding their range and moving to temperate regions, as are various diseases and disease-carrying organisms like ticks, mosquitoes, and nematodes, increasing the prevalence of illnesses like Lyme disease, West Nile, and malaria. And this goes for diseases that affect crops too. Another impact on agriculture is that plants and pollinators are emerging at different times, leading to insect die-offs in unpollinated crops. What's more, here's an impact of climate change on fisheries, ocean acidification. This happens when carbon dioxide combines with water in the ocean to form carbonic acid, lowering ocean pH and making it more acidic. This impacts the larval development of key seafood species like tuna and lobster, decreasing their survival rate. The warmer, more acidic waters also cause corals to bleach and become more brittle, essentially killing them, as well as the reef ecosystems they support. That's a lot of impacts. So what can we do? Unfortunately, there's no single solution for stopping or reversing climate change. But in a nutshell, decrease CO2 levels wherever possible. Some ways you can cut your own carbon emissions are by driving and flying less, having fewer children, eating less meat, especially beef, and using less power in general. Deforestation also takes away trees that remove CO2 from the atmosphere. So go ahead and plant some trees, native ones, that is. But that alone won't solve everything. We as individuals can only do so much. Companies and corporations have far more power and influence not only socially and economically, but environmentally. We need to make greater use of alternative energy sources like nuclear, wind, solar, and hydrogen. We can reach out to companies and encourage them to enact large-scale reforms to energy and transportation. Your dollar can go a long way. You can also contact local politicians and urge them to address climate change in your city or state. Don't underestimate the power of changes on a local scale. They can add up. Experts don't know how long we have until the consequences of climate change start to get out of our control, but some estimates place a deadline around 50 years from now. In the grand scheme of things, that's not too far away, but it does mean you have the rest of your life to make a difference. And there's no time like the present.
Okay, there you have it. So more expansion on the concept we covered. People asking for in-person training. Ask Roof Forum, but again, I think it's going to be very expensive. Okay. 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 Let's talk about Enact, but before that, where was my... Oh, okay. Okay. So remember yesterday I talked, I think everybody's back now. I talked about the map rooms yesterday. Remember for the climate analysis to extract some information. you will need to use your own tools. But if you don't have your own tools, or if you are too lazy, you can use some ready-made climate information products for some countries. I said Enactus countries. So what are Enactus countries and what's Enact? I think it's good to, do I have, okay. So Enact stands for Enhancing National Climate Services. It's something I lead here at Columbia University. The whole idea of Enact is to improve data availability, access to information products, and then help people to understand and use that information. We work with national image services to do this. And of course, the main focus is to have the best possible data for applications at a local level. So Enact has like 3 pillars. The first one is data, okay, improving data, because climate data is the foundation of any climate service. Anything you do with climate data is the foundation. So first, we work with national image services to make that happen. Once you have the data, it's not enough. It's good to have product that people can access and use. That is enhancing access. Finally, yeah, it's good to have nice maps and graphs online, but people need to understand and use those products. So we need awareness raising, capacity development, even involving users in development of the product. So this is all about Enact. And Enact is an approach, and for those 3 pillars, availability, access, and use, we use different tools. So CDT, yesterday I told climate data tool, another tool called automatic automatic weather station data tool, climate prediction tool. This is for the improving availability part of things. For improving access, we have data library and we have map rooms, which I will show you some examples. And then for use, this is support tools and curricula. Like I said, I showed you the first name. We develop some curricula to train people, especially the first curricula is actually for the agriculture experts. And CDT, I told you yesterday, I don't want to repeat it. Automatic weather station is actually, again, in many countries, they have different systems, automatic weather station. Each system sits on different computers, and it's headache to organize data in one place. And ADT does that. So it's about ADT, the PyCPT. Again, this is the forecasting side of one. This is the map room, again, told you about, for providing access. We'll have a look at part of that. And of course, the training, capacity development, all the way from professional development to university level. And this is the university curriculum I showed you on the first day, not the university, the extension curriculum. I showed you that. These are the main outputs from Enact. For now, over 40 years of rainfall temperature time series at 4-kilometer resolution. Of course, those tools, the information product, the map room I talked to you about, and of course, capacity development, both for people who generate the information and people who use the information. So these are the Enact's coverage globally. It's mostly in Africa, as you see. So the brown one is at regional level. Okay, only regional level means we don't have Enacts at country level. So the green and yellow or orange are the ones at national level. I think Nigeria should be yellow now. We just finished implementing Enact in Nigeria. So Nigeria should be the same color as Niger, Mali, and Ghana. You can see Africa, we haven't done many parts of Africa, still behind. So mostly Eastern Africa and Western Africa, and some countries in South America and a few countries in Asia, but mostly our work has been in Africa. Okay, now that is Enact. In terms of the map room, these are the, if you see the link here, it is linking to the country. So the map rooms are country map rooms. They are from the regional side agreement or the country level. You can have a look. And let's say any country, we can, if you go to Kenya, for example. Okay. So this is Kenya. So it's online. This is from directly from KMD, from Kenya. You can see the location. This is not IRI. This is directly from the Kenya Meteorological Department. So the map room, they have what we call generic map room, which is the climate map room. Okay. Climate map room, but also specific application specific map room for health, for agriculture. Actually, in some countries, I'll show you. If we go to Ethiopia, for example, if they are online, sometimes power goes off and they might not be online. Come on, okay. We're thinking. Let's go to, what about Mali? Yeah, Mali is okay. Mali is online, so they have climate and agriculture. What about Ethiopia? Let's check Rwanda, for example. Are they online? Yeah. So what do they have? They have climate, malaria, agriculture, what? Some specific information. I thought Ethiopia has more information, but it seems like Ethiopia is not online. Somebody should wake them up. So sometimes it is online, sometimes it's online. There are also regional level. So agreement for West Africa, sometimes they work, sometimes it doesn't. ICPAC for Eastern Africa. I want to show the Ethiopia map because it has a lot of information, but let's go to Kenya for now. So Kenya, like I said, you have climate and agriculture, malaria. Ethiopia has water, disaster, different. In climate, if you go to climate, remember the other day, there are 3 different kind of climate information, right? Information in the past, monitoring information, and then monitoring for climate information on the future, that is forecast. So you can see climate analysis here is for the past. We'll come to what is in here. Climate monitoring is the present, which is supposed to be updated every 10 days at least. Of course, climate forecast about in the future. So for climate analysis, you can have a look at, so you can do daily level analysis, 10 daily analysis, monthly analysis, seasonal analysis, trends, extreme temperature, you can see a lot of things. So if you want to look monthly, for example, that is if you want to look at seasonality. Okay, this is Kenya, which is the rainfall in Kenya for January. You can see it here. You can change here from month to month or even do animation. But also you can look at the grid point, or you can look for wards, sub-counties, even counties in Kenya, if you want to. So if I say wards here, so it will give me list of wards in Kenya. So if you know your ward, you can choose from here. If not, just click anywhere in Kenya. See? So it is telling you now for that, what? Okay. So this is observation for Intima, westward, Imenti North sub-county in Meru, because now this is interactive, okay? So it is making the graphs and the maps on the fly because it doesn't know I was going to choose this. So, but it is now, come on, it should give me the, yeah, so now it's a little bit slow. It should give me the information for that specific word. Okay, what about Rwanda? Let's say, I don't know, maybe go to the climate and agriculture map room. So if you see climate and agriculture for Rwanda, so daily analysis, this is where you see number of dry days, wet days, Why not look at it? So here you see you can look at daily rainfall, right? But you can also look what is it, my parameters? Rwanda, okay, this one. Okay, this one, total rainfall, right? So you can have total rainfall, but you can also look at number of wet days, rainfall intensity, number of dry spells, number of wet spells. So you can look at a lot of things. Okay. Go back. Okay, forget Mali. Where is Kenya? What's happened to Kenya? Okay, something's wrong with Kenya, but see, this is the rainfall variability over the last 40 years for that county, dry but relatively wet. Let's choose what's happening for. Okay, no, this is not it. Okay, so again, you can look at. You can also look at the mean, or you can look at probability of exceeding. What's the chance of having this many rainy days, this many dry days, this many dry spells, wet spells, a lot of things. You can also look at onsets, historical onsets for agriculture. Okay, so you have to define, there are a lot of parameters you define here, which we don't have time to go through. What's wrong with Kenya? I was looking for, okay, let me try another one. This happens when the computer is very slow. Let's say if it works for the El Nino map from here, seasonal rainfall, what? Enso, Tertiary, okay. Let's see if it works. In the meantime, so these are the onset days. So we define how we define onset for Rwanda. We said, what did we say? From 1 September, 60 days. So said it should start in September, look for until 60 days. This is the rainfall amount, and this is like actually defining what onset is, how onset is defined. And here is how cessation is defined. So here, because we said September, starting from September 1st, this is what you get here. So onset starts here for Rwanda and ends somewhere around here, because this is 4 September, 8 September, 60 means what? This is almost in November kind of thing, the onset around here. And you can click somewhere in Rwanda and see when onset happened the last how many years, when cessation or end of season happened. Okay, so this is, and so for Kenya, let's say March, April, May season, March, May, April, May season, what is the probability of being dry when it is La Nina? By the way, people following it, or I'm just talking to myself? Hello, good afternoon, good evening. People following? Let me see what the reaction is. I haven't seen the reaction. Yes, good evening. Yes, okay, okay. We are trying to follow. Yeah, I know I am fast, but this is public, so you can play it with. I just wanted to introduce it to you. Otherwise, you can go and do it yourself. Okay. So this is a lot of information. So here, for example, this is Kenya. So now here is the chance. What did I say? For the March to May season, what is the probability? It will be this season, March, April, May season, be dry during La Nina. And you see the percentile here, you see? So it seems like most of northern Kenya is what? About 50% of probability, and even some parts of southern Kenya as well, being dry during La Nina. But you can also click any of these locations and see what actually happened over the last 30 or 40 years. Okay. Hopefully it will work. Where are we in Rwanda? So Rwanda, So this is ending dates. But here it seems like the criteria is not satisfied. What do we do? This is the OND, October, November, December season. So it seems the criteria is not satisfied. So this is probability of having cessation date after, like, what? Our cessation date is what do we say? Starting from December. So 10 December, 20 December, 30 December. What's the probability having cessation end of season after 30, before 30, after 30 December? So actually it means it normally ends somewhere early December. But here it didn't like the onset. Let's try another location. So sometimes when the criteria is not satisfied, that's the issue. What about Mali? What do we have for Mali? So Mali climate. Let's just do the monthly climate. Oh no, so Mali we should do French, no? Let's say French for Mali. Okay. 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 So climatic decade, climatic mensuelle. See? Do this for Mali. I want to show you how to look at the seasonal cycle using the monthly analysis. Okay, Rwanda, at least you can see certain onset dates for certain years when actually onset happened from all the way to 1981. But anyway, you have to play with the parameters here to tune it to your area. So what's I don't like this version, but anyway, let's see what it is giving us. What about let's say map room, climate. I want to seasonal. Where is monthly analysis? Monthly. Let's Rwanda. Let's choose sector, district, maybe sector, district, province. I don't know which one. Let's do sector, small one. Okay. Okay. So this is seasonality for a given sector. You see the name, it is the location of the sector. So this is rainfall, the monthly rainfall climatology. So it seems like this area has really very long season, actually. It's only dry during June, July, otherwise mostly wet. So it comes two overlapping seasons, this part of Rwanda, with a maximum in March, April, May, but also has some October, November, December, also some season in between. It gives you a good idea. This is a climate variability over the last 40 years. You see certain dry years here. I'm suspicious of this, but then some wet and dry years here. But if I look at the southern part of Rwanda, maybe the same thing. Okay, so it's the same thing for Mali again. So is one location in Mali here. It shows you for that location. This is the rainy season is mainly June, July, August, September, with August being. You can see we are trying to change the graphics. If you compare these graphics here to this here, they're a little bit different because now we want to move toward this one. So I think Mali will be having eventually a better graphics as we go forward. Again, Kenya is having some issues. Now at regional level, ICPAC, let's see what ICPAC has. If I'm interested at the regional level, this is ICPAC. And this is, like I said, monthly climatology. By the way, you can download these graphs and the maps, okay, eventually. Here it is showing blank because it's showing January or something. Instead of January, if you say July, it will give you the rainfall climatology for July for Mali. So this we are trying to use, like I said, different graphics, but it has its own challenges. But you can see for Mali. But didn't I say French? I said French, but it's still showing me monthly reference climatology. Okay. So ICPAC again. So ICPAC, you have climate, agriculture, malaria, and in climate, you have so many things: climate analysis, monitoring, climate forecast, climate change, even, which we don't have in many countries. So again, if you're interested, like if because the data is different, right? Because the quality of the data for ICPAC is different than the data quality for the countries. The countries, because you work with them, they have the best data quality. But even ICPAC has, for example, for rainfall, they use chips, but I think they don't have temperature. So if you see climate analysis, here is rainfall. Actually, they have temperature. Okay, here. Okay. So anyway, you can have a look. This is again Mali. Like I said, climatology for July. I don't want to spend too much time on here. We are almost done. Sorry, I have to rush around because I just wanted to. It's not training. This is just exposure that there is this amount of information out there for free that you can download and use for. For example, you want to plan something in Mali or Senegal or Ghana, Ethiopia, where they have these map rooms. You can go to your ward, your warada, your whatever, and actually see the climatology, see probability of being dry, wet during La Nina, El Nino. You can do a lot of analysis, even doing the trend analysis, remember? In climate, you can see monthly analysis, but what is that? Extreme analysis, you see trend analysis. You can see what the trend has been over the last, I don't know, 20, 30, 40 years. Rainfall, temperature, probability of extreme rainfall being above this, below this. You can do a lot of things. You are all professors, so I think it's good for your students. I mean, if you want to give them an assignment, if you want them to explore some aspects of the climate of their country, their region, or their district, I think this is a very good information. Hopefully, like I said earlier, we want to expand into other countries eventually. And please do the end of training evaluation. Any question now, next 5, 10 minutes, any question, anybody? About what we have done until today, from Monday, not Monday, from Tuesday until today. If you have any question, you can raise your hand or you can write something. You can also do the evaluation. David had pasted the evaluation in the chat box. Please, if you can do that. Manuel, can we calculate monthly climatological potential of evapotranspiration? So, for Manuel, for the potential evapotranspiration, you need more than rainfall and temperature. And we have started adding those parameters for some countries, Ethiopia being one of them, Senegal. I think now we are going to add it for Kenya. So once we are able to add additional variables like relative humidity, wind, pressure, solar radiation, then we will be able to calculate potential for evapotranspiration. And then I think we can add that to the math eventually. I think that is one of the very important things we need to add, Emmanuel. I mean, I'm not sure about again, the best data, temperature data you can have is from Ethiopian Meteorological Institute because we worked with them to create this data. So I think you can, for research at KILT, I think you can you can ask them. I think they can give you the data for research. It should be free. Globally, I'm not sure for temperature. I think some of the data in what is that? The European Union. I forgot the center in the European. Copernicus, yeah. Copernicus, I think they have some data, but I've never evaluated them, so I cannot say this is the best. Okay, very good question. How reliable are the data used for those maps? The data at country level are the most reliable ones. Why? Because, like I said, we worked with them to combine the station quality control the station data, combine the station data with satellite or analysis data. That is the best data you can get anywhere. Okay, I mean, it's not when I say the best compared to other things. So even within a country, it depends where you are in the country, where you have good station, relatively good station distribution, you have good data. But in general, the country map ROMs are based on the data we worked with them to develop. So it's good data. I can download the link. I don't know the software. Software, what software? Adam Traore says software. Which was software talking about? I don't know. So the link plus. What link? I mean, okay, let me, if it is a link to the map room, those country, let me put it here, paste it here. I think maybe that is a good thing. Where is this coming? So this is the Enactus link where you can find any more information about Enact, but also the country map room, the regional map rooms. So if they don't work one day, don't give up. They might work the next day. Because sometimes power could be out or something. So let me paste in the chat that link. Here it is, okay? Enact this thing, have fun with it. Okay? Okay. Yeah, okay. I just pasted the link up. Shadia, okay. Umar, any WhatsApp group link? I don't know what's the group, WhatsApp group talking about. Anybody else with anything? Okay. I don't see any other question or comment. And I didn't check anybody I didn't see anybody raising their hands, but anyway, I'm going to check. Okay, maybe not. All right, so I'm done from my side. David, you want to say anything?
Yes, Dr. Tufa, thank you very much. I think we have done well. I've shared the link for end of training evaluation. Please, everyone, try to complete it. It's short and the questions are straightforward, so you can quickly fill it out. I've also shared on chat the recordings for all the 4 days of the training, so you can access them at any time. They will not expire. They are on our YouTube page. Then for certificates, we shall check the attendance, and then later on we can send you a soft copy of the certificate. It's just a certificate of attendance, really. It's nothing much. It's not so unique. So we shall send it to you at a later stage. Otherwise, For the materials, we shall upload the materials on the Forum e-learning platform. We are still finalizing a few things with it. So once it's ready, we shall share with you. The good thing, we have all your mailing list, so it will be easy to share it with you. Otherwise, Dr. Tufa, I think that is it from our side. Thank you so much for the wonderful presentations, and the knowledge is very insightful. And I really encourage all especially the university staff, to borrow a leaf and get some of this information and share with your students. I'm sure it will stimulate more knowledge and more discussions regarding climate. So from the forum side, thank you so much to the participants. Thank you to our facilitator, Dr. Tufa. We are always pleased when we get experts like you sharing the knowledge with the broader network. They really appreciate this. It is one of the feedback we got, and I think we shall continue doing that each time we get an opportunity. So before we go off, can people show their videos before we go off? Is that possible? David, my colleague, David, maybe can, I don't know if it's possible to activate.
No, this is a webinar.
This is a webinar format. Okay.
Yes.
Okay. Okay. All right, that's fine. Anyway, thank you, everybody. Hopefully, you over the last 4 days, you have got a couple of things from this. Like I said, it's good to share what I know with you. Like I said, I mean, it would have been better if this happened in person, but I also understand, like I said earlier, it's not easy to bring over 200 people in one place for a number of days of training. But maybe something that the countries can get organized themselves. Forum can help, but it's something that maybe better be done country by country instead of continent-wide.
Yes, I agree. It's better at country level. Yeah. We have tried a few. We did for one at Zambia and one at Ethiopia as well. So okay. It's better at country level. Yeah, so if you like the universities in Ethiopia or in Ghana, Mali get organized, it would be good again to do at that level. Number two, so remember the first day I showed you climate basics is just one module out of 4 modules for extension, or out of 5 modules for university curriculum. So it would also be good to think about if you come across projects, for example, to do something, also even adapt the whole curriculum instead of just climate basics also. Again, that something can happen at national level. You can work with Roof Forum to do that, or individually by the country. So either climate basics, but the whole module, either the extension one or the university one, could be very useful for me. I mean, if you see what climate basics is, just one module, you can see what the other modules could be. So anyway, keep in touch and have a great weekend. Thank you for Roof Forum. Thank you for the Davids for hanging around and helping out. Enjoy your weekend, everybody. Bye, ciao. All right, thank you. Bye, everyone.